Welcome to Time Series Forecasting with ARIMA and SARIMAX in Python. We will explore how to use Python for forecasting time series data, focusing on ARIMA and SARIMAX models. By the end, you will know the basics of time series analysis and how to apply two powerful forecasting methods. Running the cell now. Let us get started. You can try typing out as we go. Let us first make sure warnings do not distract us. We are also checking that our main libraries are available and ready. This line hides Python warnings for us. Now, let us see which versions of Python and each main library we are running. First comes System, which helps us check the Python version. Pandas handles tables and data frames, similar to spreadsheets. NumPy is for fast math with arrays and numbers. Stats models provide statistical analysis tools including ARIMA. Matplotlib lets us create charts and plots. Now, we print out the Python version in use. And next, we print the Pandas version we have. Let us see the stats models version. We print the version for NumPy too. Running the cell now. Try running this to make sure your environment is ready for time series forecasting. What is time series analysis? A time series is simply a set of values tracked over time, like sales each month, temperature each day, or your daily step count. Time series analysis is about finding patterns, trends, and forecasting future values. Running the cell now. Think of time series as a record of something changing, like money in your bank account every week. Next, let us load a small real-world dataset of monthly airline passengers. We label this cell as Data Setup. Here is the direct URL for the dataset. We load the dataset into a Pandas data frame, parsing dates so months are recognized and used as an index. We print out the shape to see the number of rows and columns. Let us also look at the first few rows for a quick preview. Running the cell now. Practice, try changing the URL to another time series CSV and see how the preview changes. Before any modeling, it is always helpful to visualize the data as a line chart. We are going to plot the number of passengers over time. This draws a simple line chart so we can see overall trends and patterns. We set a label for the vertical axis, which shows number of passengers flown. We label the horizontal axis to show time. Finally, we render the chart to screen. Running the cell now. Try this step on any real-life calendar data, seeing the line helps spot weird jumps or cycles. Core ideas: trend, seasonality, and noise. Trend means a long-term move higher or lower. Seasonality is a pattern that repeats, like big sales in December. Noise is just the remaining randomness after we handle trend and seasonality. Knowing these parts helps us choose the right forecasting model. Running the cell now. As you see more time series, notice if they show trend, seasonality, or mostly noise. Let us split the time series into trend, seasonality, and randomness with a built-in function. We import a tool from stats models that breaks a time series into trend and seasonality. Here we decompose the passengers column. We tell it the data repeats every 12 months, using a multiplicative model, which is good for growth data. This draws separate plots for overall trend, repeating seasonality, and noise left over. Now, let us display these parts. Running the cell now. Try changing period to 6 or 4 and see what happens to the seasonal part. Stationarity means the data does not have a changing average or variance over time. Let us plot rolling mean and standard deviation to visually check for it. We compute a 12-month rolling mean, which smooths values to spot overall trend. The rolling standard deviation shows how much values vary, also smoothed over 12 months. Draw a new figure for our plot. Plot the original number of passengers in blue. Plot the rolling mean, showing how the average changes. Plot the rolling standard deviation, showing how variation changes. Show a legend so we know which is which. Display the combined plot now. Running the cell now. For forecasting, a flat mean and standard deviation help models work well. Do you see a steady shape or big swings? Next, let us run a stationarity test. The augmented Decomposing test checks if our time series stays consistent over time. We import a function that tests for stationarity. We run the test on our passenger data. The test returns a statistic we can use. Printing the p-value tells us how sure we are. If the p-value is below 0.05, we likely have stationarity. Then we print a short message confirming it. If the p-value is higher, we say the series is probably not stationary. Running the cell now. You can try this with your own sequence. If the message says not stationary, modeling may need extra steps first. If a time series is not stationary, a common fix is differencing. This means subtracting each value from the previous one. We create a difference column by subtracting each month from the month before. We drop missing values that appear at the start. We make a new figure for our plot. We plot the differenced values over time. The chart is titled to show this is the first difference. Now, we display the plot. Running the cell now. Try differencing twice if the first difference is not enough to remove trend or seasonality. Let us build our first ARIMA forecasting model. ARIMA stands for Autoregressive Integrated Moving Average. We import the ARIMA class from stats models. We split our dataset into training parts and testing parts. Testing the last 12 months lets us see how our model works on unseen data. The ARIMA model takes three numbers. The first sets how much we use past values, the second says how many times we difference, and the third controls smoothing over errors. We train our model on the training data. We then forecast the next 12 months. We make a new chart. Draw training data in blue. Draw testing data in green, which is what really happened. Draw our forecast in red for easy comparison. Add a legend to mark which line is which. Give the plot a title. Show the visual so we can compare prediction and reality. Running the cell now. Practice, change the order values and see how the forecast line moves. What if your data has a clear seasonality pattern? Airline passengers go up and down with the time of year. Simple ARIMA cannot handle this repeating shape. SARIMA and SARIMAX models help add seasonal cycles to forecasting. Running the cell now. If your data has regular up and down changes, let us try a seasonal model. Let us switch to SARIMA, which stands for Seasonal ARIMA. This model lets us set a seasonal pattern, like repeating every 12 months. Import the SARIMAX class, which also handles SARIMA models. Build our model using the same training data, but now including a seasonal order to catch yearly patterns. Fit, or train, the model with the data. Forecast the next 12 points, just like before. Make a plot to compare training, testing, and forecast lines. Plot training values on the chart. Plot test values to see what really happened. The SARIMA forecast is shown with a dashed line for contrast. Add a legend explaining the lines. Set the title so we know this model includes seasonality. Show the final plot. Running the cell now. Try changing the seasonal period in seasonal_order, for example, try 6 or 4 for other cycles. SARIMAX lets us use outside influences to help our forecast. These are called exogenous variables. For example, marketing spend or weather can affect sales. Here we make a simple variable that just counts months. This is only for demonstration. Build SARIMAX with seasonality and add our extra variable. Train the model on training data and the exogenous input. For forecasting, make a matching future exogenous variable. Predict 12 months with this extra information. Draw a chart of all 3 lines. Plot training data first. Add real test outcomes. Add our SARIMAX forecast in a new style and color. Add our legend. Title the chart to show we used an exogenous variable. Finally, display the plot. Running the cell now. Try feeding in real external data for better results, like temperature, advertising, or economic signals. To know which model does best, let us measure error. Mean absolute error, MAE, tells us how far off, on average, our forecast is. Import the mean absolute error function from scikit-learn. Get the MAE for ARIMA prediction versus real results. Calculate MAE for SARIMA. Do the same for SARIMAX. Print the ARIMA error score, rounded to 2 decimal places. Print SARIMA error to compare. Print SARIMAX error for reference. Running the cell now. Which model had the smallest error? Lower is better. Mini project, forecasting future shampoo sales. You are the manager of a store. Use a similar Python process to forecast shampoo sales next 12 months. We will load data, visualize, and forecast using ARIMA, SARIMA, and SARIMAX. Running the cell now. Try to follow along. See if you can spot trend and seasonality in this new series. Let us switch datasets and load monthly shampoo sales. We set the link for this new data. Load it in just like before, using months as our index. Rename the column to Sales for clarity. Show the shape to see how much data we have. Print a few first rows to preview. Running the cell now. Can you spot any missing or strange values in the preview? First, always look at the new data as a line chart. Make a time series plot for shampoo sales, no legend needed. This chart shows months along the bottom, sales up the side. Label vertical axis as sales value. Label months across the bottom. Show the finished plot. Running the cell now. What pattern do you see? Does sales grow or fall? Is there a repeating cycle? Let us forecast the next 6 months of shampoo sales. We split the data, train 2 models, then draw their predictions versus real values. First, we split the shampoo data into train and test sets. Train with all but last 6 months, test with the final 6. Fit an ARIMA model, order 111, like before. Fit a SARIMA model with yearly seasonality using SARIMAX. Get a 6-point forecast from each model. Next, generate prediction with SARIMA 2. Plot training sales as a baseline. Add the true test values. Plot the ARIMA forecast line. Plot SARIMA forecast for comparison. Legend helps pick out each line. Title the chart for clarity. Display the comparison plot. Running the cell now. Challenge, try using a different forecast window or changing model order to see what changes. It is easy to add too much complexity, which fits noise and fails on new data. Keep model orders as low as possible for small datasets. Try a higher but still simple model order. Set the seasonal order with yearly cycles. Fit the SARIMAX model using these orders. Predict next 6 months just like before. Print out our test forecast values for review. Print the actual numbers so you can check by eye. Running the cell now. See if these forecasts look more or less realistic than simpler models. Sometimes, models refuse to fit. Common errors mention invertible or parameters. Do not panic. Try different order values or check for missing data. If something goes wrong, wrap the model in a try block to catch the error. Here, we try a weak model which may fail. If the model crashes, print the error message clearly. This last comment reminds us that model settings matter for a good fit. Running the cell now. If you get an error, read the message and try a different set of order values. Recap. What have we learned? We loaded and visualized time series data. We explored core concepts, trend, seasonality, stationarity. We built ARIMA, SARIMA, and SARIMAX models for forecasting. We measured model accuracy and tried a mini-project. You have the basics to keep experimenting with real-time series. Running the cell now. Try bringing in your own data. See what patterns and predictions you find. Keep learning with us. If you enjoyed this, subscribe for more step-by-step Python tutorials. Share your experiments in the comments or ask us a question below. Happy forecasting! Running the cell now. Let us keep growing together, subscribe and join the learning journey.